Einstein now asked, if acceleration and gravity are equivalent, what happens while accelerating that reveals something new about gravity? Back to his rocket ship, Einstein resumed his thought experiment. As the rocket accelerates, a ray of light shining through the window hits the other side at a lower point than it entered. To a passenger, the light appears to curve. If acceleration can bend light, then by the equivalence principle, gravity must do the same. It seemed a crucial clue. But where would it lead?
Gravity does more than make things fall. That much was clear. But I still had no idea what it was. My office in Prague looked out over an asylum, and there were times when I felt a certain kinship with the inmates. They were the madmen who did not concern themselves with physics. I was the madman who did.
The asylum is still there, walls, bars, inmates, and all. For his part, Einstein was only half joking. Over the next 5 years, gravity became almost his sole obsession. In 1912, Einstein broke with Elsa and moved to Zurich to teach at the ETH, the Federal Polytechnic where he and Mileva had studied. Einstein had been an undistinguished student. Now he was coming back as a full professor of theoretical physics. Here he embarked on the most intense effort of his life, renewing his attack on the gravity problem. He started with an idea from a former teacher, Hermann Minkowski, who had doubts about his troublesome pupil until he read Einstein's 1905 paper on special relativity.
Minkowski called me a lazy dog, and perhaps he was right, but relativity seemed to impress him. I would have felt some sense of triumph, only then he translated it into mathematical terms, whereupon even I couldn't understand my theory.
Einstein may not have understood it, but to Minkowski it was clear. Space and time are fused together into a single four-dimensional picture of the world. Here is one of the most common space-time experiences, meeting a friend on a summer day. This meeting takes place at a particular location, the intersection of the two paths, and, one hopes, at a precise time, 10 minutes past 10. As Minkowski recognized, every event forms a unique mathematical picture in space-time. Here, as the seconds pass, the man stays in one place in space, but moves continuously through the time dimension until his date arrives. As the idea of space-time sunk in, Einstein realized he could go one step beyond. He asked, what if the shape of space and time could warp and curve? What would happen then? His answer, gravity happens.
Einstein's brilliant idea, the idea that makes the whole thing work, was the fact that it is matter and energy, which drives the bending of space and time. Throw a rock into a pond, for example. When you throw a rock into a pond, ripples start to form. It is the rock which creates the ripples on the surface of the pond. Therefore, the presence of a rock creates ripples in space and time that we call gravity.
Space-time without matter is flat, but add a rock or a star and the whole picture changes. The enormous mass of the star creates a huge dent. Anything that passes close enough will roll down and around that warp in space-time. That's gravity, the straightest path through the curves in space-time created by matter and energy. It was this picture that showed Einstein how gravity holds the Earth in orbit. The Earth simply follows the warp in space-time created by the sun. Einstein published an early version of his new theory of gravity in 1913. There were still pieces missing, but he impressed the one audience that mattered. In that year, Max Planck, Germany's leading physicist, made the pilgrimage to Zurich with a colleague to offer Einstein a job in Berlin.
Planck and Nernst looked me over as if I were a prize hen. But I didn't know if I could lay another egg. I told them I needed to think about it and would meet them at the station the next day. If my answer was no, I would wear a white flower in my lapel. But if the flower was red, then Berlin it would be.
It was the climax of a career. Berlin was the world's leading center for theoretical physics. Without doubt, the former patent clerk had arrived. He faced one last hurdle. He could not solve the mathematics of curved space-time. The problem had stumped him for 3 years. Einstein's friend was Marcel Grossmann, his college classmate whose math notes he had once borrowed. Grossmann again tutored Einstein, this time in the complex geometry of curved surfaces. It took Einstein 3 years to master all the subtleties.
Let's see where he introduces this further.
By the fall of 1915, he was ready to put the theory to the test. The orbits of the planets were understood with extraordinary precision, with one exception. Mercury's orbit shifted slightly, unaccountably, every year.
When I found that my calculations predicted the motion of Mercury exactly, something snapped inside me. The feeling was so extreme. I couldn't work for days. I was beside myself. In all my life, I never felt such joy.
The calculation vindicated Einstein's radical idea that space-time is curved. Mercury, the innermost planet, shifts its orbit as it travels around the dent in space and time created by the sun's huge mass. Mass everywhere deforms the space around it. Even light, as Einstein had recognized years before, must follow all the curves in space and time, mapping the shape of the universe as a whole. It is this understanding that drives the scientific story of creation. The Big Bang, the expanding universe, the structure of galaxies, the great sweep of modern cosmology derives directly from this single equation. Space and time on the left, matter and energy on the right. This is the general theory of relativity, Einstein's theory of gravity.